Welcome to clickmyproject.com. The title of this paper is Parallel Frequent Item Set Mining with Selective Item Replication. This comes under the domain data mining. The main concept behind this paper is the frequent pattern mining. That is, mining frequent item sets, that is, patterns or anything from data transactional database is said to be frequent item set mining. This comprises the core of several data mining algorithms such as association rule mining and sequence mining, etc. These mining algorithms are too time consuming process and more cost consuming process. In order to avoid those disadvantages from the existing techniques, many parallel frequent item set mining techniques have been proposed. Ours proposed is also one type of parallel frequent item set mining which achieve better flexibility and efficiency. There are many disadvantages in the existing techniques. They did not answer to the following questions such as: can we design a parallel algorithm that exploits data parallelism and task parallelism? And another one, can we find a model to optimize its performance? Our proposed paper gives an affirmative answer to these questions by introducing an algorithm that divides the database into independently mined parts in a top-down fashion according to an optimized distribution of the item set. Our proposed work also uses a new approach called GPVS, that is graph partitioning by vertex separator problem, where the partitioning objective corresponds to minimizing the data replication or collective work by setting appropriate weights to vertices, and the partitioning constraint corresponds to maintaining storage balance or computational load by setting appropriate weights likewise. Thus, our proposed work has the advantages like less time consuming process, cost effective, and it is a load balanced process, and is a parallel frequent item set mining process. Now I will explain the proposed concept. In this proposed concept, we introduce two new coarse-grained data parallel FIM algorithms using a top-down data partitioning scheme with selective replication. We propose a novel divide and conquer strategy suitable for parallelization of the FIM task. This objective is to divide the whole transaction database into parts that can be mined independently. It turns out that we can distribute items so as to achieve our goal of independent mining while replicating some items selectively, implying an amount of work that cannot be divided further in the same fashion. Now I will explain the concept detailed which is used in this paper. Let's assume a transaction database like this, and this is the representation of that transaction database, and this database is represented in a graph format according to the support count of each items present in that transaction database. After performing this, we will apply a GPVS partitioning method to split this graph into different parts. Here we will split the graphs into two by choosing one separator. That separator is chosen based on one condition. That condition is that the subgraphs must be in a balanced weight. That is, if we sum all those values present in this, it should be both subgraphs should be less than the entire graph's weight, and it should be in a balanced manner. Likewise, we will split the graphs according to some criteria and will obtain a final set of graphs like this. And this is the splitted graph, and here is the separator. Likewise, we will split the transactional database into two. Finally, after splitting the graph into two, we will find the item sets that are present in each subgraph. Each subgraph is mined parallelly to achieve less time consuming process and a cost effective process. For that, we will use no click and no click 2 algorithm. These two algorithms are the base algorithms that are used in this paper. In no click algorithm, we will perform pattern mining algorithm. That is, we will perform tree construction based on the items present in the transactions. We will form the prefix tree, and the prefix tree is searched over the breadth first order and affords fast candidate generation in a fashion similar to KDCI. We use a regular tree data structure instead of prefix arrays as in KDCIs. Fast candidate generation relies on the fact that the prefix tree already captures much of the proximity between two item sets needed for generating a candidate. To speed up, we will develop a TID list for each transaction. That is, whenever we will calculate which item is present in whichever transactions. Likewise, we will form a TID list. To speed up the TID list insertions, we use a cache to hold all the TID list intersections in the path to the root, so that a single additional intersection is sufficient to count the transactions in candidate item set. The overall algorithm is quite efficient. Its performance is comparable to other existing systems, and it is better than those existing systems. After performing no-click, we will continue with the no-click 2. The no-click 2 will be performing four steps. It will redistribute the items with selective replication, and it will mine replicated items in parallel and mine non-replicated items independently, and then finally merge the frequent item sets across replicated and non-replicated sets of items. The phase of this algorithm ends with these 4 steps. Now I will explain the flow of this. We will select a transaction database, and for that transaction database we have to draw the graph. The graph is constructed according to the item count, that is the number of items present in the transaction database will be collected, and the occurrence of each particular item will be collected, and according to that the graph will be drawn. From that graph we will choose the separator. Separator will be chosen in a manner that it will be checking the transaction database load, whether the subgraph A's load is must be in approximately equal to the subgraphs B's load. After splitting the graph, we will be now having a true transactional database. Then we will select final item sets from the final splitted graph. For that we will apply no-click algorithm and no-click algorithm 2. The no-click algorithm, in the sense we will be applying that TID list insertion, and we will be constructing a tree, and from that we will mine a set of items. For that set of items we will redistribute the selective replication, and we will mine replicated items in parallel and mine non-replicated item independently, and finally merge all those results in no-click 2. After performing this, like above said, replicated items are mined parallelly and non-replicated items are mined independently. Finally we will merge those results, and the final item set is obtained now. Now I am going to show the demo of this project. For that we need NetBeans and WAMP server. After starting the WAMP server, open the project in NetBeans and select home run file and select, and the project will get executed now. The form will get open. In that the transactional database will be displayed. Yes, initial data. This is the initial data which is, and we will be analyzing that, and the result will be, that is will be calculating the each item count, and for that we will be constructing the graph. The transactions are identified and the notations have been set for that, and the threshold is set, and the values which are greater than the threshold is selected, and for that we will be computing the graph. Next we will be proceeding with the separator selection. The separator is selected now and the graph is partitioned, and for that subgraph we will be calculating this is the weight of the entire graph, and this is the subgraph A, subgraph B, and this is the subgraph A's weight, and this is the subgraph B's weight. And after performing that we will be collecting the transaction items in both the subgraphs, and we will be finding the support count for that, and we will be sorting in a ascending order. Then we will be constructing the tree, that is TID list insertion. For TID list insertion we have to construct a tree. The level of the tree is 4, and this is the TID list for 1 and 2. From that the patterns are mined, and after that T1 patterns is listed, and this is for replicated items mining parallelly and non-replicated items, and same way for T2, and finally we will be obtaining the resultant patterns from this. From this our proposed work ends, and this is the parallel frequent item set mining. Thanks for listening the project. Thank you.